I'm going to be explaining a problem that I really liked called correct placement. And it's a really nice problem because it's just nice, just a nice problem. So just read the problem and then we'll get to it. So essentially, what you're trying to do, in a nutshell, is that assuming you've already read the problem, pause it. Um, in a nutshell, for a rectangle, you're trying to see for a rectangle I. So for this the rectangle, or let me even just do a better example actually. So for rectangle I, right, you're trying to see can the you're trying to find any other rectangle J. So I'll do this in another color. Any other rectangle J such that J can strictly fit within the bounds, not touching, but within, so you can't touch the bounds of I. So can you put rectangle J and rectangle I in a way such that they don't intersect, right? A rectangle I has to enclose rectangle J fully. That's the question. So for each rectangle, you're trying to find at least one other rectangle J such that you can put rectangle J inside of rectangle I. Um, and notice that and here is at first I read this condition, I was like, okay, that's not that bad. The condition that kind of throws you off is the fact that you can rotate the rectangle so that it does fit into rectangle I. So let's say the orientation they give you in the problem is this, right? Is rectangle, let's do this, right? Let's say it's this, right? You notice that for this rectangle J, you can actually rotate this rectangle. Like if I rotate J 90 degrees, right? Then the rotated variant of J can fit inside rectangle I. So when you're looking for other rectangles, you need to also realize that um you basically can if it doesn't fit initially, like with the initial orientation, you can rotate it so that it does fit in rectangle I. So the question now is, when is it optimal to rotate a rectangle? How do you know when to rotate a rectangle? Because obviously, since n is 10 to the fifth, essentially, um, and then you can't just do an n squared solution where you take every two rectangle and then you try every single orientation of rectangles. Like you can't do that. So you need to ask yourselves, when is it optimal? When is it like how what orientation is optimal for a rectangle? And this is actually the tricky part, but I'll try to kind of derive this instead of like prove it. I will prove it, but we'll derive it first. So how do we kind of like figure this out? Well, we notice that, like, let me put it back up here. We notice that we're trying to fulfill these inequalities, right? So to fit rectangle J inside of rectangle I, we have to formally at least one of the following conditions must be fulfilled: this one or this one. I don't really get thrown off by standing or lying down. It doesn't matter. Like we don't care. Doesn't really, like a rectangle height and width, they don't mean anything. Which brings me up to a good point. If we're trying to fulfill these inequalities, like instead of like when they give us like when they give us a for a rectangle I, they give us h sub I, and they give us w sub I, right? Technically, this doesn't necessarily for this rectangle I. H sub I, the actual value placed there, doesn't actually have to be the height. Like I could easily just do w sub I and h sub I because I could rotate it, right? You can rotate it so it's like this. So like, do I actually care that this is the height, and do I actually care that this is the width? No, because you can rotate it so that like so that it's not the height and it's not the width anymore. The what you actually care about in the context of comparing two things, you care about the size of the actual value of the actual value of the height and the actual width. You actually care about the size. And what I mean is that instead of doing h sub I, w sub I, we should really think of it as, is it s sub I, b sub I, or b sub I, s sub I, where s of I is less than or equal to b sub I. What I'm basically saying, should we put the smaller dimension first, or not dimension? Should we put the smaller value first, or should we put the bigger value first? Because in the sense of comparing things, why I don't really care should I put the height first or the width first, right? It doesn't, like, height and width don't mean anything. Like, so like you can't just ask yourself, should I put the height first or the width first? Because like for example, here what I'm trying to say is that if you had an example like 2 6, right? Should the height go first or the width go first? So should it, like should I do 6 2 or 2 6? Well, like, this isn't, like, I could have another example like 6 2, right? I could have two rectangles, and if I ask myself, should the height go first or the width go first, right? If I say that the width should always go first, then I'm going to have 6 2, and then I'm going to have 2 6. If I'm saying that the width should always go first, well, I've just contradicted myself, because I said for this rectangle, like these are basically the same rectangle. This, like, let's say this is I and J, whatever. Like, I and J are the same rectangle. Like, they're just, one is the rotated version of the other. If I say that it's always more optimal to put the width first to orient a rectangle such that the width is first, well, then I know that I've just contradicted myself, because if I put this width first here, it's 2 6. If I put this width first, it's 6 2. So I'm saying that 6 2 is more optimal, is optimal, is the most optimal, and 2 6 is the most optimal, and that's obviously a contradiction, because only one should be more optimal, or we don't even know yet. We don't know yet that if orientation actually matters. Obviously, it does, though. Like, I just showed you that orientation does matter, because this case, like, you have to rotate this rectangle so that it does fit. So orientation obviously matters. But here, I just contradicted myself here. So the question shouldn't be like, should you put the height or width first? Because in essence, height and width are the same thing. The real question is that in this case, should I put the 2 first and then the 6, or should I put the 6 first and then the 2? So, and the only difference between those in the context of inequalities is um is is which one's bigger? Is the 2 bigger or the 6 better bigger? Cuz I don't care how tall J is, right? As long as it still fits within I. Like, I don't care if it's this or this, as long as it fits in I. So in a sense, you only care about what is the small number or the big number. So that's kind of the rationale, the intuition of this, like, kind of method that I'm using. So for all rectangles, we won't, since height and width are the same thing, like I just said, we will only care for rectangle I. Should we do S of I or B sub I, right? And so for rectangle I, we're trying to fit the rectangle J. So the question is, should we orient it in terms of um S sub J, B sub J, or um uh sorry, B sub J, S sub J? Like, which one? So which combination is the most optimal? Now that's what we ask ourselves, which combination will allow us to have success, because our goal is trying to fit rectangle J inside of rectangle I. So which one will allow us to have the most success, having this guy and this guy, or having this guy and this guy, or having this guy and that guy, or having this guy and this guy? Which situation allows us to do, to essentially fit the rectangle the best, right? To have most success, right? Because, like, this doesn't look like an optimizing problem, but, like, in the sense of that, we're trying to see, like, which orientation is the best, because we don't have, like, we can't just try both orientation. It's just, you need to see when you should swap a rectangle, like, or when you should swap the arguments of a rectangle or keep it the same. So how do we do this? Well, let's just look through every single case, right? Like, I literally, there's only four, so, like, it doesn't hurt. So let's look at this case. So case one, you have, if you look at this case, well, then in order to fit rectangle J inside of rectangle I, then S sub I must be greater than S sub J, and B sub I must be greater than B sub J. All right. So let's look at the other case. Let's do it this. So case two, we know that S sub I has to be greater than B sub J, and B sub I has to be greater than B sub I has to be greater than S sub I. Sorry. So essentially, these two are just swapped, right? That's case two. and you'll notice that the other cases are basically are the same. Like if I want to compare now b sub I and this case, so like case three, you have the same comparisons. You'll still compare b sub I with b sub j, right? And you still compare s of I so with s sub j. And then if you do it like this, I think the diagonal. I think um I think the other one that we didn't try was the diagonal. You'll still have the same comparisons. Like you're still gonna compare s sub I with b sub j and b sub I with s sub I. So these are the only two cases that you actually get if you go through all four of them. The question now we ask ourselves, which one is more sort of like quote unquote optimal? Which one will allow us to actually fit the rectangle inside of um which one will allow us to fit rectangle J inside of rectangle I more successfully in general? Like, or does this even matter? Like, and the question is, like, intuitively, your intuition should lean to one more. And here's why I'm going to say that I mean, it's intuition. I can't really just say your intuition should be this. It's intuition, but I'm saying like intuitively, one should be more successful than two. Because think about it like this, right? If because both of these conditions have to be true, right? So okay, sure, this condition's more wait, this should be J. This should not. This should be J. My bad. So yeah, if you thought this was I, that's my bad. This should be. Hopefully, you could kind of figure that out. But yeah, this should be J. But obviously, this condition is more likely to occur. Like this condition is more likely to occur than this one, right? Obviously, but then we know that this condition um for one is more likely to occur than this condition. So then you're like, it's not too obvious. Just looking at it, it's not too obvious because one condition, like in both, there's one condition that's more likely to occur than another condition in one condition in the other in both scenarios, scenario one, scenario two. But so like then it's kind of like hard to see like which one's like more fitting. Well, like intuitively, one should be more fitting. Like why? Because think about it like this: like an analogy is analogies are for sure not like a proof or anything, but like if you're playing 5v5 basketball, it's always more optimal to put the smaller guys on the smaller guys and the bigger guys on the bigger guy. Nobody plays 5v5 basketball, like at least if you're playing good 5v5 basketball with like a good coach and stuff, the coach doesn't put the big guy on the small guy and then yeah, the big guy on the small guy. Like the coach doesn't do put their big guy with their small guy, and then put no put our big guy with their small guy, and then put our small guy with the big guy. That doesn't make sense. You don't do that. Coaches in like in the NBA or even in anything, or just really not even has to be sports. Like it just makes more sense. Put the small guy on the small guy and the big guy on the big guy. That's the matchup. That's the more optimal scenario, right? So it should be your intuition should think that one is more optimal than two. So then that motivates us to make the claim that one is more optimal than two. So claim. Now we make the claim that one is more optimal than two. Now, since this is coding and not math, you could technically code this, but if you're still like worried that this might like since there is a penalty in Codeforces, you kind of have to sacrifice the penalty and time. If you're in a time crunch, might as well just code it and but like there's only two I like so because there's the other scenario is that two is more optimal than one, or the orientation doesn't even matter, which the third scenario is kind of like obviously false. It does matter. So how do we prove this? Well, like this kind of took me I actually did not figure this out by myself. Um, I kind of had help, so I won't lie when I say this. But to prove this, although I did have the intuition that this is obviously more optimal because of like the analogy I made, but to prove this rigorously, like this is kind of I guess nah I don't know. Assume that two is true, right? Assume that two is true. if you assume that 2 is true, then you have S sub I is greater than B sub j, right? And from that we can say that, and which is true, because that's, if 2 is true, then then this is true, right? Because this is, these are the conditions in 2. So then you can say, and you also know that B sub j is also greater than B sub S sub j. It should be greater than S sub j. And you know that S sub j, you know that B sub I is greater than S sub j, but you also know that B sub I is greater than S sub I. Like B sub I is greater than S sub I, right? And then B sub I is obviously greater than S sub j, right? Um, hold on. But I had to pause. Well, yeah, I don't know where I was. Well, assume, yeah, if you assume 2 is true, then you have this. So you know that this is basically the like inequality statement you get from 2 if you assume 2 is true. Well, you also notice that if I assume 2 is true, then 1 is also. Because look, S sub I is greater than S sub j, S sub I is greater than S sub j, B sub I is greater than B sub j, B sub I is greater than B sub j. So assuming 2 is true, makes that it also makes 1 true. So for every instance that 2 is true, 1 will also be true. So we've already proved that 2 it does not have any advantage over 1, because even if 2 is true, then 1 is also true too. So we've proven that 2 has no advantage over 1. But we also ask ourselves, does this mean that they're equally likely to occur? Well, let's assume that 1 is true then. Let's assume 1 is true. If they're equally likely to occur, right? Which is not our claim. Our claim is that 1 is more likely than 2. But if they're equally likely than to occur, then we should say if 1 is true, we should also expect 2 to be true. Because it has to go both ways for them to be equally likely. So then the idea is that if you assume 1 is true, you get the statement S sub I is greater than S sub j, and you also know that this is B sub I, and B sub I is greater than B sub j. You know that you have these two statements, but like you need to, like, there, you'll notice that when you do this, like B sub I is greater than B sub j, there are no, like, you can't combine, like there's no way to combine these statements such that you guarantee to, because B sub I has to be greater than B sub j, and then I need, like, but you notice that you can't say, and B sub I, so this has to be true, but, and you also know that B sub I is greater than S sub I. Like, that is true, but in order to combine these statements like we combined them last time, I have to put like this, so that B sub I is greater than S sub I. You notice that you can't do that, because you're not guaranteed that B sub j is greater than S sub I. There's no guarantee in scenario 1, or in case 1, such that is true. So you'll figure out that there's no way to arrange, and I don't know how to like write this mathematically, but there's no way to arrange these, to unite these inequalities such that you can make 2 true always. So if 1 is true, 2 isn't necessarily true. You'll see that there's just no way that, because the last time we were easily able to like arrange it such that we're guaranteed 1 is true, but 2 isn't necessarily true. So the idea is that you can design instances where 1 is true but 2 is false, but you cannot design instances where 2 is true and 1 is false. Therefore 1 is always more advantageous than 2, and 1 is always more quote unquote true than 2. So if 1 is always more true than 2, then now we've proven that you should always, so now this is the proof, 1 is more optimal. So we've proven that a rectangle should always be in the form of S sub I, B sub I for all I, because we know that. So essentially, when you're given the like these rectangles like 3 4, 5 4, and 3 3, you always, like, for example, you always need to keep the smaller one first, and if there's no smaller one, then it doesn't matter, right? You always need to keep the smaller one first. So for example, for 5 4, when we process 5 4, we're going to actually make this into 4 5. We'll basically rotate it. So you only rotate a rectangle if and only if the first argument is bigger than the second argument, because you need to make sure that the smaller argument is actually first. So that is the proof. And if you do that, you know that any comparison will always, you will always have the best comparison possible. Therefore, you can basically apply the rotations if needed, and then you don't have to worry about this condition where can you have to you can rotate a rectangle. You can just solve the problem regularly. So this is a big part of the problem. But now, how do we actually solve it? It still takes time. Like, this is not even, the problem's not even finished. We still need to actually solve this, and it's not that bad. Essentially, what you do is, like, let's say you had person one, like person one, person two, right? Or let me do rectangle one actually, because I've been calling them rectangles, not people. Let's say you have these people. So, I guess I'll do seven of them, right? Let's say you have these seven rectangles, whatever. How do we actually do this in linear, in like log n log n or linear time? Well, one thing you can do is you can sort it by height. So you can sort it by the first argument. And I'm not even going to call them by height, because you're not sorting it by height. You can just sort it by the first argument, which I guess we'll call it height. But like I said, height and width don't mean anything. You can sort it by the first argument. So in fact, we'll actually call it, so for a rectangle R, which is S sub I, B sub I, you sort everything by S sub I, right? If you sort everything by S of I, that means if I go to rectangle 4, I know that all these people have a smaller s, and these people have a bigger s, because I sorted it by s, right? I sorted it by S sub I. And if I sorted it by s, right? And we need to make sure that these people are basically, like, we only care about people who have a smaller s than us. So these are all the possible candidates for J, and so J has to have a smaller s. So we only care about this side. So we don't care about the bigger people. We only care about this prefix. And then basically, what you need to do is, if all these people are smaller, then the best candidate, or the best J, is the person with the least width, or basically, because we also need that J has to have everything smaller. So the person with the least B is the best. So if person two had the least B, then you only care about person two, because you're already guaranteed the fact that this has a smaller S. You're not guaranteed that it has a smaller B. So in order to have like the best, optimize the best case, right, is obviously just to take the guy that has the least B and then compare the least B and see, is the least B smaller than this person four or whatever. And so this might be a little bit tricky because of the edge case of the person, um the person that, like, if you get to person four, right, you only want to keep track of the minimum, the least B, if that person had a different height than yours, right? Because it could like this still, like, let's say person four had a height of four, person three could have a height of four. So if it has the same height, you don't want to keep track of the minimum width, or the minimum, if it had the same S, you don't want to keep track of the minimum B. So in order to like deal with that edge case, you just use a pointer, right? So the idea is that for this person, for person one, we'll look back and we'll say, um does this person have the same height as me? It does. There's obviously no one there, so we keep the pointer to be -1, right? And then you go to pointer two, right? Does this pointer have the same? Does this person have the same height as me? If it does, then you keep the pointer at -1. You don't move the pointer. If it has a different height, then the pointer is at 1. And basically the pointers basically, like, for example, let's say we get to person four, right? And let's say that person three had the same height as me. That means that the pointer should be here, or wherever it had a different height, that means you only want to you only want to take the minimum of this prefix from person one to person two. So the pointer basically keeps track of which prefix you should be looking at the minimum for, and you can already, if you want to, you can essentially like pre-compute the prefix minimums and then have the pointer that tells you where you should where you should reference the prefix minimums. Because you, like, if you go to person four, right? um you, like, if person three has a different height than you, then okay, that's fine, then we just reference the prefix minimum from one to three, from like um 1 to I minus 1, or whatever. But if they had a different height than you, then we don't want to reference that. So wherever it was kept last, that's where we're going to reference. So we'll reference like wherever it was kept last. That's where we're going to reference the pointer. And yeah, that's basically the solution. You just check if to if to if this if when you're trying to get the answer for P4, if P3 has a different height, then you can reference from P1 to P3. If it doesn't, then you can't, and then you just take where it last was. And that is the solution. But honestly, the big thing was just proving that you should always rotate a rectangle if the first argument is bigger. That's the hard part. This part is usually, that's not that bad. And yeah, that's it. Thanks for watching.